Welcome back. So we have been defining again some reaction terminology, right. So what is enthalpy, what is standard enthalpy, what is enthalpy of a reaction, what is enthalpy, the reference enthalpy, right. So of any standard elements, pure elements, and based on which we can define enthalpy of any compound, right. So with a particular value, right. So because I have a reference now, the reference is 0 at H naught at 298 Kelvin for all the constitutive pure elements is 0. Okay. Now based on this, let us look at some chemical reactions, right. So any chemical reaction is going to look like A plus B gives rise to C plus D, right. And I am going to ask you to compute, let us say I know the enthalpy, right. So the delta H reaction at some temperature, right. So at let us say 298 Kelvin and or some temperature T1 P1, right. And I am going to ask you, based on this, can you compute delta H reaction at T2 P2. Okay. Now what is delta H reaction at T1 P1? That is Hc plus Hd, right, at those temperatures and pressures, right. So if it is standard, then it becomes H naught, right. So if it is 1 atmosphere, then it becomes H naught, right, minus Ha plus Hb. Right. So that is what is called the delta H of reaction, right. So we are now formally defining it. What is delta S reaction at T1 P1? Exactly the same thing. So Sc plus Sd minus Sa minus Sp plus Sp, right. And delta G of reaction is going to be delta H of reaction minus, right, T delta S of reaction, right. These are all standard terms and standard terminologies, delta G. Okay. All right. So now I want to calculate the, so for sake of simplicity, let us just take, I have delta H of reaction at a particular temperature and 1 atmosphere, right. So that is delta H naught in some sense, right. Then T1, then I want to compute delta H naught at T2. Okay. How do I go about doing this? So I have to, so I have so I have to do H, each of these is combination of several different reactants, right. So I am going to say H C at T2, H naught C at T2 plus H naught C H naught D at T2 minus H naught A at T2 minus H naught B at T2, right. This is the delta H reaction at T2, right, minus H naught C at T1 so H naught C at T1 minus H naught A at T1 minus H naught B at T1. This is what I need to compute, right. So this is what this this is the delta H reaction at T2 and this is the delta H reaction at T1, right. Or this is what, okay, so this is equal, okay, so this is what I have, this is what I know. So I do not need to minus it, this is what I need to compute. Right. Now this is the information I have. Okay. Now for me to go from T1 to T2, so I need to know how delta H changes as a function of temperature, right. So how does H change as a function of temperature? Sorry. Let me just right. So, how does H change as a function of temperature? That is just Cp dt, integral Cp dt, right. Now, let us say there is a phase transition, right, H naught H naught T2 minus H naught T1, right, Cp dt from T2 to T1, T1 to, okay, let me rewrite it. Okay. So, let us see H naught T2 minus H naught T1 for any material, any compound is integral Cp dt from T1 to T2 plus, let us say in between T1 and T2 there is a temperature T P. At Tp there is a Tp which is less than T1 T2, right. So, which is in between T1 and T2, and at Tp, you know, so this is HA undergoes a phase transition. If A undergoes a phase transition, I have this plus the phase transition terms or the latent heat terms. Okay. So, this is the recipe I am going to use, right. So, to go from T2 to T1 I have to do this, right. So, now I have this entire thing delta H naught of D at T2 minus H naught of D at T1, right, plus H naught of C at T2 minus H naught of C at T1, right, okay, minus of H naught of A at T2 minus H naught of A at T1, right, minus of H naught of B at T2 minus H naught of B at T1. I think I am just unnecessarily belaboring it, but you know, so it is, and that is equal to delta H reaction at delta H naught reaction at T2 minus delta H naught reaction at T1, right. So, now what is this? This is nothing but Cp of D, right, integral Cp of D T1 to T2 plus integral Cp of C dt T1 to T2 minus integral Cp of A dt T1 to T2 minus integral Cp of B dt T1 to T2 plus any sort of latent heat contributions, right. Now, you know, that just becomes Cpd plus Cpc minus Cpa minus Cpb, right, dt from T2 to T1 to T2 plus any sort of you know, latent heat contributions, right. And this term I am going to define it as some delta Cp of the reaction, right, at you know, delta Cp of the reaction from T2 to T1, at T2 minus delta Cp of the reaction at T1. Okay. So, this is how I am going to define this. Okay. So, effectively now I know, right. So, so essentially delta H I can write a very terse reaction, delta H terse equation at T2 comma 1 atmosphere is equal to delta H naught of the reaction at T1 plus delta Cp of the reaction which gets integrated from T1 to T2 dt plus any sort of phase transition latent heat contributions. Okay. So, this is what I can derive for delta H naught. Similarly, if I write you know, delta S naught, right, at T2. I want to find delta S naught at T2. When I know delta S naught reaction at T1, right. Now, it does not need to be delta S naught, I can also do this at any other pressure, right. So, pressure I am just fixing it for 1 atmosphere just to be just not to confuse you or anything, but ideally this can be extended to any pressure, plus integral Cp by T now dt delta or delta Cp reaction by T dt from T1 to T2 plus any sort of phase transition latent heat contributions. Okay. Now, let us do an example, right. Now, the example is that of let us say lead oxide. Okay. So, the reason why I take lead oxide is there is a nice phase transition that happens here. So, we will be able to put in the phase transition also. Okay. So, lead liquid plus half oxygen gives rise to lead oxide. So, let us say I want to make lead oxide at 800 Kelvin, right, and this is a reaction happening at 800 Kelvin 1 atmosphere, right, and I want to compute delta H reaction at 800 Kelvin and 1 atmosphere, right. All right. Now, at 800 Kelvin H naught of lead liquid, H naught of oxygen is not 0, that is 0 at 298 Kelvin, right. Now, I give you some information, I know the delta H formation of lead oxide. At 298 Kelvin, that is equal to that is some number, right, this I know. Okay. And at 298 Kelvin, so lead is in a solid state plus half O2 gives rise to PbO, right. So, the delta H formation of lead oxide is the delta H of this reaction that I know, right. So, what is H naught 298 of lead solid, that is equal to 0. This is a standard state is there solid, right. So, it is not liquid, but it is a solid state. Okay. H naught of oxygen at 298 Kelvin, that is also equal to 0. So, the delta H formation of this reaction is H naught of lead oxide solid at 298 Kelvin. These are one and the same, or delta H of that reaction. Okay. Now, B, lead melts at 600 Kelvin, right, and I know the latent heat of fusion of lead. Okay. Now, it is easy, right. So, now I exactly these two are known, right. So, this is known, this is also known. Okay. So, then delta H of the reaction at 800 Kelvin is equal to delta H of the reaction at 298 Kelvin, right, plus integral 298 to 600, right, Cp of lead oxide solid minus Cp of lead solid, right, minus half Cp of O2, correct. So, this is the delta Cp of reaction dt plus from 600 to 800 what I have is not solid lead oxide, but Cp of liquid lead oxide, okay, minus Cp of lead solid and oxygen continue, okay, dt, and these Cp's can be read off from tables, right. So, the getting Cp's is an easy job, right. So, it can be read off from thermodynamic tables plus delta H fusion of lead that occurs at 600 Kelvin 1 atmosphere 600 Kelvin. Okay. So, this is the latent heat term. Okay. That is it. So, I know this term, I know this, Cp's can be read from thermodynamic tables, okay, and then so delta H fusion is something that I have given you, right. So, this I know, this I know, this I know. So, I can estimate the delta H of reaction at 800 Kelvin. Okay. So, all right, let us move on. Okay. So, now let us go to example 2. This time let us calculate the entropy, right. Now, let us consider sulfur. Okay. This is sulfur. I will write it as FUR, maybe it is PHUR or something like that, right. Sulfur exists in two phases. One is what is called the monoclinic phase, one is what is called the rhombohedral phase, right. Okay. Now, we have to so monoclinic phase is stable at temperature less than 369 Kelvin. Rhombohedral phase is stable at temperature greater than 369 Kelvin, which means at 369 Kelvin, right, there is a phase transition. Okay. Or in other words, S mono transforms to S rhombo. Okay. Now, what does this mean that there is a phase transition at 369 Kelvin, right. So, let us so let us look at what are called reaction coordinate diagrams. Okay. Now, there is a reaction going on. So, I have an appropriate potential for that reaction, right. So, and that appropriate potential, let us say, is free energy, some kind of free energy, right. So, Helmholtz free energy or Gibbs free energy. Now, what I am saying is at let us say 298 Kelvin, so I am going to write it as this is my monoclinic phase, this is my rhombohedral phase, right. This is delta, this is G, right, and G naught, because I am doing this at 1 atmospheric pressure. Now, what I am saying is there is some pathway to go from monoclinic phase to a rhombohedral phase, right. So, I have to change some structure of sulfur, right. So, I have to, so sulfur is in some monoclinic arrangement like this, right. All these are sulfur atoms, they have to go to some rhombohedral arrangement which is, let us say, much more symmetric, right. So, there should be some kind of first I have to nucleate, let us say, sulfur in this region, and then I have to propagate that nucleation further. There is some process by which this happens. There is some process, and that process I am going to call it as reaction coordinate, right. There is some reaction coordinates that are changing, right, which means so this nucleation reaction coordinate is changing and it is propagating, right. So, so essentially I can quantify this process in terms of what is called a reaction coordinate, which is what chemists use all this while, all the time. Okay. Now, at 298 Kelvin, right, we see that the Gibbs free energy of the monoclinic phase is less than the Gibbs free energy of the rhombohedral phase. That does not mean if I put sulfur in the rhombohedral phase, right. So, this is the state, so this is the system occupies this state, so I should still give it some energy, right, called the activation energy for the system to jump from the monoclinic phase to rhombohedral phase, right, which means at 298 Kelvin monoclinic phase is the stable phase, and by stability what I mean is the most stable phase is is the global sorry, let me just write it like this. Okay. But that does not mean a rhombohedral phase is not a stable phase. Rhombohedral phase also so it has if I look at the dg is equal to 0 here, right. So, rhombohedral phase, I mean as a function of the reaction coordinate of course, right. So, the rhombohedral phase is also stable, but G naught rhombohedral is less than G naught of monoclinic, right. So, this is a globally stable phase, but if I can get my sulfur stuck to being in rhombohedral phase. I can do something so that I free sulfur in the rhombohedral phase, right. So, then this is called a metastable phase. It has some stability, it is not that it is not stable, right. So, dg is equal to 0 as a function of the reaction coordinate, right. So, thermodynamically I go towards dg equal to 0. So, there is some stability there, right. So, this has some stability, or I mean in a and so dou square g by dou x square should be greater than 0, that is the other thing, but so dg is equal to 0, that means my R phase is a stable phase, but it is a metastable phase. And given enough energy, or what is called the activation energy, and how much is that activation energy? This is the monoclinic phase, this is the rhombohedral phase, I give this much of energy, this is delta G A. Okay. So, given enough activation energy, R phase goes to a more a globally stable M phase. Okay. So, it can actually flip from here to here given enough activation energy. Okay. So, this is the scenario at 298 Kelvin, right. So, I can somehow give some energy, not necessarily thermal energy, let us say I apply some stress or something like that, so that I can maybe make the monoclinic phase a stable the rhombohedral phase a stable phase at 298 Kelvin. Then I remove the stress, or so I give it enough and then it is stable there. Once I remove the stress, it stays there. I should give it some other form of input so that the rhombohedral phase goes to a monoclinic phase, right. So, this is the understanding of these kinds of reaction coordinate diagrams. Okay. Now, what does it mean that at 369 Kelvin I have a phase transition? That means at 369 Kelvin the stability, or so the absolute values of G naught of mono and G naught of rhombo are the same. Do not get me wrong, both of them have stability, right, but both of them are equally so the absolute values of G naught tells me what is the most globally stable state, right. If G naught is really small compared to G naught of rhombo, then mono is stable, is globally stable compared to rhombo. Given enough energy to rhombo, it will go to mono, right. But if the system is in rhombo, then it will stay in rhombo, right, so until you disturb it from the rhombo state. Okay. Now, greater than 369 Kelvin, the rhombohedral phase is more stable, I mean has a lower free energy, right. So, this is mono, this is rhombo, right, and less than 369 Kelvin, it is the other way around, right. So, this is mono, this is rhombo, right. So, ideally so I can go from rhombo to mono just by changing the temperature, but then you have to still provide the kinetic barrier, right. Let us say it is in a rhombohedral state, right. I reduce the temperature, it is still in a rhombohedral state, right, unless I provide this kinetic barrier delta G activation, right. So, this is what is called the kinetic barrier. It cannot go to the monoclinic phase, right, but the kinetic barrier has reduced by reducing it below the phase transition temperature. The kinetic barrier has reduced that the rhombo, the globally stable phase happens to be the monoclinic phase. Okay. Now, in this context I am going to do this reaction, right. What is the reaction? Reaction is S mono but I am going to do this reaction at 0 Kelvin, right. At 0 Kelvin, the globally stable phase is monoclinic phase, right. So, this is mono, this is rhombo at 0 Kelvin, but that does not matter. If given enough activation barrier, I can still push from mono to rhombo, or so if I am already in the rhombohedral phase, given enough activation energy, I can come from rhombo to mono, right. So, that is how I interpret this, right. So, I can go from one reaction coordinate to another reaction coordinate. Okay. Now I want you to estimate the delta S of the reaction, right, at 0 Kelvin. This is the reaction, okay. S mono goes to S rhombo, or the other way around, S rhombo goes to S mono, okay. Now, what do I know? Do I know the delta S of reaction at 369 Kelvin? Yes, because what is the delta G of reaction at 369 Kelvin? At 369 Kelvin, G naught of mono is equal to G naught of rhombo. This is at 369 Kelvin, right. So, if the reaction is S mono to S rhombo, delta G of the reaction at 369 Kelvin is equal to G naught rhombo minus G naught mono, which is equal to 0, right. So, I know the delta G of the reaction at 369 Kelvin, that is the phase transition temperature, right. So, G naught, so that is what. So, at phase transitions, the delta G's of reactions are going to be zeros, right. So, the reaction does not know whether to proceed this way or that way, right. So, I am not, typically they proceed towards reducing delta G, but delta G itself is 0. So, the reaction, so I have to perturb it a bit, so that one becomes more favorable than the other, right. So, if I reduce the temperature, then monoclinic becomes more favorable. The G naught of mono is less than G naught of rhombo. But if I tilt it the other way, then rhombo becomes more favorable than mono, right. So, this is I am changing the equilibrium conditions, okay. All right. So, now delta G naught of the reaction, delta G naught of the reaction at 369 Kelvin is 0, and that is equal to delta H naught of the reaction at 369 Kelvin minus T delta S naught of the reaction at 369 Kelvin, right. At 369 Kelvin, what is delta H of the reaction? This is the latent heat of phase transition, right, because there is a phase transition happening at 369 Kelvin. So, delta H naught of the reaction at 369 Kelvin is nothing but the latent heat of phase transition, okay. Now, what is that? That I have a value for that, I can tell you. So, the value of so this is delta H of the latent heat of so let us just, it is solid to solid reaction, right. So, they also have latent heats. So, I am just going to call it delta HL is 96 calorie per mole, not kilocalorie per mole, okay. So, in that case I know the delta S naught of the reaction at 369 Kelvin, right. This is equal to 0, this is delta G naught at 369 Kelvin. As a result, delta H naught is a value that I know. So, delta S naught is nothing but 96 by 369 calorie per mole per Kelvin, okay. So, I know 1 S naught, right. So, I know the S naught of the reaction at 369 Kelvin, right. S mono to S rhombo right. I know the delta S naught of the reaction at 369 Kelvin, and that is equal to 96 by 369 calorie per mole per Kelvin, okay. So, this is the information that I have, okay. Now, I want to conduct this reaction at 0 Kelvin, right. So, for me to conduct this reaction at 0 Kelvin, I am just going to say so delta S naught of the reaction at 0 Kelvin is equal to delta S naught of the reaction at 369 Kelvin, the value of which I have, plus integral Cp by T, right, dt of from T the higher from the higher temperature 369 Kelvin to 0 Kelvin of rhombohedral phase minus integral Cp by T dt from 369 Kelvin to 0 Kelvin of the monoclinic phase. Okay. Now, so I need these values essentially. I need the Cp of rhombohedral phase, I need the Cp of monoclinic phase, and Cp is a function of temperature, right. Cp is only at very high temperature Cp becomes independent of temperature, but Cp as a function of temperature, right, of the monoclinic phase of the rhombohedral phase. If only I have this information, I will be happier, right. And indeed, so people have computed, like I said, there are thermodynamic tables where people have computed such information. Let me just get that for you. You can actually get the citation of this paper, right. So, it is the heat capacity and you can download it yourself, heat capacity and entropy of rhombic and monoclinic sulfur, right. Let me zoom it up, okay. And so you can actually read this paper to see how people were measuring Cp's, and this was a paper that was published in 1937. So, we had this data from 1937, the Cp's of sulfur, right. So, in the monoclinic phase, in the rhombohedral phase were there since 1937, and people know how to measure these Cp's, right. In fact, you can see this table, this is of a rhombohedral phase. It starts at about 10 Kelvin, right. So, it is not exactly 0 Kelvin, but it starts about 10 Kelvin. So, people knew how to do these measurements, and then there is a chart of Cp in calories, of course, as a function of temperature all the way up to 400 Kelvin, right. So, and the data table is also here, okay. And similarly, this is also rhombic sulfur, but if I look at the monoclinic sulfur also has, this is the monoclinic sulfur, Cp of monoclinic sulfur as a function of temperature, right. At various temperature the Cp per calorie per degree, right. So, of the monoclinic sulfur is there. They have calculated delta Cp, not just delta Cp by T, right. So, that is what we need delta Cp by T dt, right. So, they have already calculated all these things for us, and this is how the Cp of monoclinic sulfur is, okay. Now, if I do this calculation, okay, and so the reason why I am showing you these tables is these tables are standard, right. So, they are already there, people have measured Cp's and measured Cp's over a range of temperatures, right. So, that material property is well established, right. So, Cp is well established, okay. Now, Cp is well established. So, what you can do then as a self study exercise, if I am teaching a real, so if I am teaching a course in a classroom, right, so with the students in front of me, I would give this as an assignment, but here so my assignments are constrained to ABCDs. So, this is not going to be an assignment, but I want you to do this, right. I want you to actually compute this value with these data tables, right. So, it is a numerical integration, you have the tables, you go to some kind of a data plotting software, you compute the integral of Cp by T dt, right, or delta Cp by T dt between the rhombohedral phase and the monoclinic phase, and compute this value, okay. And you do it yourself, right. So, this is an exercise that you may have to do it yourself, and then you will, so what were we finding? Delta S of the reaction at 0 Kelvin, and you will see that the delta S of the reaction at 0 Kelvin is actually 0 or close to 0, because you do not have data all the way up to 0 Kelvin, you will have data up to 10 Kelvin, you will have some data up to 60 Kelvin. So, you will have to extrapolate using suitable models, but I want you to do that, right. So, I want you to do that, you take help from AI, or so if you are a bit hesitant as to how to extrapolate these Cp values to 0, right. So, there are proper models by which you can extrapolate Cp values all the way up to T equal to 0. But if you do that and then you find delta S of the reaction at 0 Kelvin, delta S of the reaction at 0 Kelvin is 0, right. And this is not just for the reaction that we considered, sulfur mono to sulfur rhombo, right. Any reaction, any phase transition, or any reaction involving crystalline solids, you can do similar exercises and you will find that the delta S of reaction, similar exercises because CPs have been computed, delta S of the reaction at 0 Kelvin equal to 0, right. And this is only possible if S of all these materials, right. So, all these let us say crystalline materials at 0 Kelvin equal to 0, okay. And this is how people came up with the third law of thermodynamics, right. So, it is not from Boltzmann, right. So, that people somehow knew S is 0, right. So, or for crystalline materials I will say what is the caveat here, right. So, people somehow knew by looking at these sort of exercises that we did, precisely these sort of exercises, right. This is in 1937, the paper that I was showing you it was in 1937, right, the sulfur mono to sulfur rhombo phase transition. And so people have computed the values of S at 0 Kelvin or values of several such reactions involving proper crystals, proper minerals, right. So, several reactions they have seen and they have computed, okay, so how does Cp change as a function of temperature, how does Cp by T change as a function of temperature of reactants of products, and then how does delta S of the reaction at 0 Kelvin look like, right. And all these reactions the delta S was 0, right. And this is possible only if S at 0 Kelvin of each of these individual components is 0, right. And that they termed it as the third law of thermodynamics. There is no other way. It comes from empirical data actually. It is not something that just came out of blue thin air, right. It's not like so Newton saw an apple falling down and gave his F equal to ma or things like that, right. So, this comes from a lot of empirical data that has been measured, and then let us look at delta Cp, right. And this predates Boltzmann, right. So, this predates the fact that S equal to K ln omega, and then omega at 0 Kelvin, so at 0 Kelvin I do not have so many states, everything is frozen, so I just have one state, so K ln omega should be 0, right. So, that is how Boltzmann explained it later on, right. However, here so this comes from a lot of empirical data, and this was before the time of AI, when I knew, so when people even knew how to understand so much amount of data, right. So the discovery, so it needs to be appreciated that so lot of data collection and then processing it through the similar sort of methodology that I said, and that is how people have come to the third law of thermodynamics, saying that okay, S of nice pure crystalline materials is 0 at 0 Kelvin. The understanding for it came from Boltzmann later on, saying that alright, at 0 Kelvin I do not have any modes of vibration, I do not have anything at all happening in the solid, all atoms are frozen, that is the definition of 0 Kelvin, right. So all my electrons are frozen, all my phonons are frozen, right. So it is all a frozen state, right. And it is just so one velocity, and that velocity is 0. So, I can do this velocity distributions and get to the fact that temperature is 0, everything is frozen at the mean velocity, okay. And so no kinetic energy, no potential, of course there is potential energy and other things, but there is no vibrations, right. So, there is only one state, and this system is accessing this one state, okay. And so, in S equal to K ln omega, omega is 1, right. So, this is I keep using a bit of StatMech, right. So, the idea is you anyway have seen this S equal to K ln omega in other courses, that omega is 1, and that means my entropy is 0 for a pure crystalline solids, right. So, that defines the third law of thermodynamics, and we came from it, so the way people have measured it empirically. So, through some empirical data of one of these examples, and that example is my favorite example of sulfur, and this paper is one of the most beautiful papers. It does not tell you any science, it just collates data. It collates data and then says alright, in this reaction delta S of reaction at 0 Kelvin is 0, right. You can do it in sitting in your homes, you can do this numerical integration now and then find out what integral Cp by T dt equal to 0. And first time I did it, I was very happy that, oh wow, so one example, it's not that, so I have done so many things by myself. One example, sit, solve, and then find out for yourself that delta S is indeed 0, and then that gives you some kind of goosebumps, right? So wow, third law of thermodynamics, it's not something that someone is teaching me and I'm listening to them, but it is something that I can solve and see it myself, right? So it's the consequence of it. I mean, it's not that so through these empirical laws, people said, all right, so S of crystalline materials is 0. Okay. Now I keep saying S of crystalline materials at 0 Kelvin is 0, which means there is a caveat to this, right? So this does not work for, or so third law of thermodynamics does not work for disordered materials. Right? It does not work for what are called spin glasses. Right? It does not work for a certain set of things that get frozen, but there is some disorder in these materials. Okay. Now the point is, so it's a very subtle point. So they have what is called, I can measure the entropy as a function of temperature for all these materials. Right? Typically, so the entropy, you expect it to go to 0. So this is for regular crystalline materials, right? But for all these disordered materials, spin glasses, relaxers, which are what are called dipolar glasses, right? There are bunch of materials, amorphous materials, right? So S actually does not go to 0 really, but S, so people, so they say that it actually saturates to some kind of, a value, and this is called residual entropy. Okay. Now does this mean these materials are not freezing completely? Are they not accessing only one state? Right. Now, all right. So now at this point you can propose some theories, right? So because the question is, how much can I measure temperature, right? So temperature equal to 0 Kelvin. Can I measure it? Can I get to that temperature? The answer is no, right? So absolute 0, you cannot really get to, right? So but how close can I get, right? So experimentally, how close can I get to temperature equal to 0 Kelvin, right? Now for day to day experiments, to get to really low temperatures, you use what are called dilution refrigerators. Now these dilution refrigerators are becoming very common, I mean very popular nowadays because of quantum computing, right. So all your quantum computing using the standard qubits that happens inside a dilution refrigerator, your qubit should be so cold, right, otherwise they'll lose their coherence and other things. So dilution refrigerators are becoming more and more popular nowadays with the advent of quantum computing, but so that's not the point here. The point we are trying to make is with dilution refrigerators you can cool down materials to up to tens of millikelvin, right. So this is so on a day to day basis, so if I have these dilution refrigerators, now dilution refrigerators themselves, so how they are constructed has a lot of beautiful thermodynamics in it, heat cycles, thermodynamics, then phase transitions between helium 4 and helium 3, these are isotopes of helium, the phase transitions, latent heats, all these things that we are talking about, right, is used in this technology to create dilution refrigerators where I can cool my material to about 10 millikelvin, let us say 10 millikelvin. Okay. Now 10 millikelvin is 10 power minus 3 of a Kelvin, so this is the closest I can get to 0 on a day to day basis. Now, so people have actually shown, so they take some kind of lasers, right, then they trap atoms, right. So they sort of make sure that there is no atomic vibration at all, right. So for by taking lasers and trapping atoms, and so then you can actually calculate the local temperature of your atomic vibrations or your phonons or something like that using a Bose-Einstein statistics, and using these sort of laser trapping techniques, people were able to go up to picokelvin temperatures, right. But this is a very local change in temperature, and so locally the bosonic or the phonons show a picokelvin temperature, but this would require complex experimentation, and you cannot really you cannot really generalize this for all materials, because you have to do very precise measurements on a local environment, right. So locally disordered materials, so I have to at least understand certain volume of this material, but picokelvin temperatures have been achieved, but it's in a very specific settings, right. So on a day to day basis, you can nowadays you can use a Dill fridge and get to 10⁻³ Kelvin. Now, in all these disordered materials, right, so if I have residual entropy, what am I saying? I am saying that this material can take in a reaction coordinate, right. So like what we have earlier as a function of reaction coordinate. One of the models I can propose is as follows: this material can take several states, 1, 2, 3, 4, 5, right, and these several states give it some residual entropy, okay, which means this material is able to jump from one state to another state to another state to another state to another state. That means there is some activation barrier here, right, and this activation barrier is less than the kT of my material, right. Now, so K, if so in a disordered material or in a spin glass, right. So what is a spin glass? Spin glass is a material where I have spins arranged in all different types of directions, right. So I have local fluctuations of spins which are arranged in all sorts of directions. So this is very glassy in nature. Now they also fluctuate, right. So the spin the spin correlated region, which is like this, in the next time instant can become like this, right, like this, right. So this is as a function of time, they will keep fluctuating. It's a huge amount of fluctuations, right. So this is not accessing just one state, but it has many such states that it is able to access. As a result, the entropy of this magnetic spin system is not 0. Right. So even if you freeze it down to 0 Kelvin, it can just jump from one state to another state, right. Now, what does it mean that it's able to show this residual entropy? That means that the number of states that this can take is more, which means that one state can jump to another state within so by getting this activation barrier, activation energy. And if this activation energy is sort of set by kT, right. So the temperature scale for this is kT. What we are essentially probably saying is between one state and the other state, this kT, right, that I have is actually much less than kT obtained by T equal to 10 millikelvin, right. So probably I should cool it down even more, so that I just freeze the system in one state, this state, right. So probably that these disordered systems, again I am making a hypothesis here, this may not be correct. The disordered systems or spin glasses have a residual entropy, may be to do with the fact I cannot cool below 10⁻³ Kelvin currently, right. If I can cool to let us say 10 power nano Kelvin, picokelvin on a larger scale, then perhaps I may see still that third law is valid for these systems, right, albeit at something like nano Kelvin, pico Kelvin temperatures. I do not know, so we do not have any proper way of getting to these temperatures on a larger scale, right. So, locally you can get through laser cooling, etc., but on a larger scale it is so difficult to get to these temperatures. So, as a result, so I cannot really say that third law is not valid. I can say that third law has not been tested out, right, and that is my experimental limitation, right. So, third law has not been tested out for these spin glasses by going to really low temperatures, okay. So, as a result, so it can so happen that so I have a residual entropy, right, which is coming like this. I sort of extrapolate, I am not going all the way up to 0 Kelvin, but I am sort of extrapolating and saying that this is my extrapolation and saying that there is a residual entropy, but it is always possible that this can go like this, right. So, this can be your residual entropy can still be 0. It is just that these temperatures, this is temperature versus S, these low temperatures less than 10 power minus 3 Kelvin have not been accessible in any sort of large scale manner, right. I cannot just, I do not have a machine where I can put my equipment in, my material in and say that this material has gone down to picokelvin temperature, okay. So, so as a result, so the violation of third law can just be that I was not able to go to low temperatures, okay. So, as a result, as of now, as we stand today, we cannot really say if third law has been violated. Rather, the correct statement to say is third law has not been experimentally proven to be true or false. You be agnostic about it, right. So, for in the case of disordered materials, right. Now, up to 10 millikelvin, right. So, if I just extrapolate this curve, there is some residual entropy, right. Below 10 Kelvin, again so it is anyone's guess, okay. Okay. So, so with that so I finished the 3 laws of thermodynamics. In the next class we will actually look at, again we will come back to these functionals. Again to get to the third law I had to introduce some reactions, right. So this is important because so that is how people have gone to the third law of thermodynamics, okay. So, it is but having said that, we will again move back to our free energy functionals in the next class and this time look at open systems, because so far we have been developing this language in the closed system, but so all our reactions, all our growth processes are happening in open systems. So, it is better now to go to open systems and then try to extend this language of free energies, the Helmholtz, the Gibbs free energies to open systems, okay. Once we do that, we are going to, to do that, or not once we do that, but to do that we would now require to define one of the most important quantities, right. So, in this course, and that is called the chemical potential, right. Read it up before you tune into the next lecture. What is chemical potential, right. So, how do you understand chemical potential, even if you have taken some materials courses, right. So, how do you understand chemical potential, and we will start there in the next class, and we will have a big discourse on what chemical potential is, and from there we will again try to expand these quantities and slowly shift towards understanding phase diagrams and so on and so forth, okay. All right. So, with that let me conclude here and I will see you again in the next class. Thank you very much.